Welcome to class. In this video, we're going to talk about exact equations. Well, what do I mean by an exact equation? Well, it's one that has this form. We say that an equation of this form, where I've got m times dx plus n times dy, and those m and n might have both x's and y's floating around. But we say this is exact as long as my, or the partial of m with respect to y, is equal to the partial of n with respect to x. In other words, some other language you might hear is that the left-hand side of the equation is an exact differential. Let's take a look at just an example of how do I tell if something's exact. Here, we want to show that this is an exact equation. It's a little easier to see in this one that this is the m of xy I'm talking about. It's whatever coefficient dx has, and whatever coefficient dy has is n. So just like x comes right before y in the English alphabet, m comes right before n in the English alphabet. That helps you remember which is which. And all I need to do is quickly verify I have this identity. My, then, is going to be 3x squared, y squared. If I bring this 3 down, subtract 1 from the power. And x is same thing over here, just taking the partial with respect to x. I get 3x squared, y squared. And what do you know? Those are the same. So this equation's exact. So what makes exact equations so special? Well, when I look at this form, to me, that immediately reads like the total differential of some function. If you recall, that's just fx dx plus fy dy. And it turns out that so long as everything is sufficiently continuously differentiable, meaning there's some rectangle R for which these m and n are in C1 of R, then there has to be some function f whose total differential is equal to this exact differential. And it turns out that a function f whose total differential is this exact differential, well, that's a general solution to the exact equation. Let's take a look at an example. In fact, why don't we just do this one and let's solve or find the general solution to this exact equation. Just going to give ourselves a little more room. So while I was getting set up here, I decided I'd throw up that total differential definition as a reminder that the total differential of some function f df is just x derivative dx plus y derivative dy. And I wanted this to be up here so that we can reference it as we look back and forth. Now, we already showed that this is an exact equation, so what we're about to do works. But what I want to look at here is, what does this imply? Really, what I'm doing in this problem is taking the total differential in reverse. I am looking for that function f, such that, well, first of all, I know that the piece next to dx, in that case, that's x squared y cubed, well, that should be fx. And the piece next to dy, x cubed y squared, well, that should be fy. So really, I have two equally good starting points for this problem. It doesn't matter which you start with. In general, if you're working problems on your own, I'd recommend starting from whichever piece is going to be easier to integrate. But for this problem, they're about the same. So why don't I just start with x, since it comes first in the alphabet. So first, I can use the fact that fx is x squared y cubed to tell me something about f. I know that whenever I integrate fx with respect to x, that should give me f. So let's take that integral. Here, I get 1/3 x cubed y cubed. But now that I have a multivariate function, we've got to be a little bit more careful. I don't just have a constant of integration, but there may very well have been an entire function of y's only, whose partial derivative with respect to x would drop. So I'm going to call that capital Y of y. Right, so I get this antiderivative, plus I might have an extra piece that only has y's in it. I'm not able to uncover that information just yet. But luckily, there's still some info from the problem that we've extrapolated that I haven't used yet, and that's this other piece. I already know what the partial derivative with respect to y should be. So let's take the partial derivative with respect to y. According to my setup, I will get, well, x cubed y squared plus whatever this function of y is, its derivative, equals, well, I already know that this should give me x cubed y squared. So now let's ignore this fy over here and just look at this piece, or this equation. I can reduce that quite a bit by canceling x cubed y squared on either side, and this just tells me that whatever that function capital Y was, its derivative is 0. What type of function has a derivative of 0? Well, constants, of course. So this tells me that I actually didn't have a function of y. I did, in fact, just have a constant. So, piecing all of that information together, I can now write my general solution as f of xy equals x cubed y cubed times a third is what we found in step 1, and then step 2 told us that this extra function of y is actually just a constant.